think you're muted.
Okay, good morning.
Okay, all right. Yeah, you ready? Okay, let's go.
Okay, well, thank you very much for the invitation to this conference. So what I'm going to say does make links with many things already said and things which will be said. But I'll probably, no doubt, forget to make some of those connections. Also, so the talk is in three parts. So in the first part, I kind of pose the problem. In the second part, I pose a solution. And in the third part, I raise various further directions, much in line with what Sherry was asking for. So there are 6 different directions which I found I have been tempted to go after I've done this work, and I raise those as things which may be of interest to others. So, okay, so I'm talking about the subject of educability, which is a concept which I define in a recent book. But just to set the scene, to start with some settled science, let's also start with Turing, and who asked in a 1950 radio broadcast whether everything humans can do can be done by a machine. And he famously answered that it's customary in a talk or article on the subject to offer a grain of comfort in the form of a statement that some particular human characteristic could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. And this wasn't just his philosophical viewpoint for Turing, this was really his science, because this was based on the Church-Turing thesis, which is, of course, one of the most solid parts of known science. And so basically he gave us a license to talk about machines and humans in the same breath 70 years ago, and kind of we should be doing this. So the question is, what's left to do? Well, if humans and machines do the same thing, what else is left to do? But of course, the problem is that we don't know what either can do too well. So the main unsettled science which I want to address is how to characterize the capabilities of either. So how good are we at understanding human capabilities? I want to kind of explicitly understand them. And certainly intelligence is the word most widely used, even at this conference, to characterize human capabilities. And the problem is that we don't know what it means. So famously, the Board of Scientific Affairs of the American Psychological Association was asked to write a report on what intelligence is, and because of its societal importance in intelligence tests, and they quoted a sentence which said that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. So this isn't very satisfactory, but it's not surprising, because intelligence was originally defined, at least intelligence as a scientific concept, intelligence quotient, implicitly in terms of statistics by Spearman. But this is, I find, very unsatisfying. I don't think the word intelligence has helped us very much to get anywhere, including artificial intelligence. And just one point, which I'm not sure whether it's trivial or profound, but I've recently noticed, so the SAT test, which many universities are reinstating. So the question is, we know what S stands for scholastic and T means for test, but what does A stand for? So you may say aptitude, but in fact that's not true. It used to stand for aptitude. That was removed. Then it stood for assessment for a few years. But amazingly, A stands for nothing now. So SAT is just a brand name. And when students take this test, no one tells them what it's about. Okay, so if you buy a grapefruit, then it's you're told it's a grapefruit, but if you do this test, you're not told what it is. The implication is that it correlates with something like performance in college, but again, when you buy grapefruit, there's more of a promise than just saying that eating this correlates with reducing your hunger. Okay, so what is the question we can ask to elicit better definitions of cognitive capabilities, which I want to do? So I don't want to define intelligence, but I want to find something which can be defined, which may be more useful. So I've written a book, and this is the cover, and I just want to advertise not the title of the author, but the design by the cover designer. So this is prehistoric axe head on the top and computer cursor on the bottom. And what the book asks is, what was the cognitive capability that enables humans to go from one to the other? So what is it? What is the capability which enables us to be different from other animals? And so in some sense, this question makes it easier than general AI, because many of our capabilities we share with other species, so we don't have to discuss vision, locomotion, emotions, etc. But it liberates us to discuss, I suppose, the disembodied computation. But this capability I call the civilization enabler. And the approach I use is computer science. So there's quite a bit of discussion in the book about why this is a good approach. But very briefly, the aspects I use is that I want what I define to be functionally well defined as input-output, and what I define I want to be computationally feasible. So this is a definite methodology which I'll use. And just a historical comment, so Herbert Simon in 1958 predicted that within 10 years all psychological theories will be based on some comparison with computer programs. So this didn't quite come about. Of course, now slowly this is coming about. So certainly my approach, which is in this direction, is heavily based on advances in computer science which have happened since then. Okay, so what is the civilization enabler? So I'm still setting up the problem here. So you can find websites where the academic papers on here 617 different topics, which are differences between humans and our closest relatives. There's no shortage of investigations of all aspects of differences in every dimension. But which one, if any, is this civilization enabler? Again, I'm looking just for cognitive capability, which plausibly has enabled us to achieve the civilization we have. And of course, so eyebrows are suggested as something unique to humans, but of course there's no theory which says that if you have eyebrows then you build rockets to go to the moon. Animal domestication. So there are many things which were very important in our history, maybe even critical, but again, there's no theory which says that if you can domesticate animals, then you can do all the other things we do. There are many other things which we're special about. So many people in the many communities who try to address this question of human uniqueness concentrate on collaboration, social learning, learning from others. But again, these aren't entirely unique to humans, and again, by themselves, they don't explain our capabilities. So intelligence, okay, good word, but we don't know what it means. Symbols language, again, these things must be getting really close, but again, just by teaching an ape language, it doesn't change its behavior. So language isn't the basic capability, and the symbols aren't the basic capability. So is this overambitious, this whole project? Well, I suggest not. So evolutionarily, one is really asking about a relatively brief step of evolution. I'm not asking for all the evolution of mammals, for example. I believe it's a brief step. So what did Darwin think of this question? Well, in one place he said that he considered these various one-word or one-phrase possibilities as being the offering human uniqueness, and said that none of them work, and we're different in degree rather than kind in any of these dimensions. So there are any number of books coming out from various communities who try to offer solutions to this. But very basically what this approach has to offer is very simple. It is that by this computer science approach, one is more precise. Okay, so one tries to be more precise than people are who have use these more general terms. And by being more precise, you can also express concepts which are slightly more complicated. Okay, so what if the answer to this question is something just slightly more complicated than, say, social learning, and something more specific? So that's what I'm trying to do. And in some sense, I think the history of AI has been along these lines, that one defines functions like learning by example more specifically, and that's productive, whereas if you just keep to general words, ill-defined words, it's not so productive. Okay, so this was the introduction. Now I'll just, in the second part, I'll describe my proposed answer in outline. So this will be a capability which is a compound capability. It's composite of several things, and I called it educability because it does remind one of a general process of gathering, of being educated. Okay, and basically it consists of three parts in a context, where the context is defined in two parts. Okay, so the first part is being able to acquire beliefs by generalizing from experience. And here I take exactly a computer science description of what this means, and basically it means, this will mean vanilla machine learning. Okay, so that's one part. So the second part is that once animals in evolution managed to do this, which was a very long time ago, I think, it was natural to combine two things which you've learned in sequence, because no action is based on just having been trained on one simple task. So, for example, Pavlovian conditioning is known to be able to chain things. So this would be chaining. So this is chaining what you've learned and applying it to particular situations. That's the second part. And the third part is to acquire beliefs which you haven't learned from experience, but beliefs which someone else has given to you explicitly. So they may be giving you a cookery recipe, a computer program, something which you can internalize and execute, a formula for calculating something in quantum mechanics, something explicit given to you by someone else, discovered by someone else. Okay, so these are the three basic kinds of activities, capabilities one has, but one has to say that this all has to be done in a rich enough environment, in a rich enough context that's not trivial. So if you can all do this for a one pixel world, that's not too interesting. So so these three things are integrated, and I'll explain all this in a second in more detail. You have to be able to analyze a multi-object scene, so we can look out and see 5 things in front of us, some relations among them, and we can learn in terms of these, and we can reason in terms of these. And also all this is also done with everything in symbolic naming, that we, for example, we can make up concepts. We aren't restricted to objects externally. Okay, so I suppose animals, dogs responding to their name is the beginnings of this kind of thing. Okay. Okay. So I won't say much of educational philosophy except to say that certainly in education people discuss rote learning in a lecture room, and this is part 3. And people discuss that hands-on learning, where you learn from experience, offers you something different. That's part 1. And the second one is the beginnings of applying what you've learned to particular situations, and also reasoning about what you've learned. So this covers some bases of educational philosophy, and says that you have to do all of these things. Okay, so I'm saying that this capability is what somehow humans acquired. I don't have to guess exactly when, where, or how, but although I don't have to, I just will. And the main point, I think, is that basically generalizing from experience is very ancient. Every living organism probably has to do something, and combining it also is. But what the new addition is this being able to receive explicitly described beliefs or formulas, programs, recipes from others, in humans mostly by being told in natural language, but you can also do it by physical demonstration. And presumably this happened, okay, so as a guess, my guess is that we already had this when our species emerged about 300,000 years ago, and some predecessor species, it somehow evolved in some predecessor stage. But I don't need the details, but the only general point here is that, so no one believes that there was any dramatic biological change in humans in the last tens of thousands of years. So we must be looking for some capability which just took a very long time to reach its fuller effect. Okay, so quickly I'll describe these 3 facets of this model. Okay, so the first is generalization from experience, which, as I said, is exactly what is practiced in machine learning quite successfully. And here the idea is that we have a learning algorithm, and it trains on labeled examples, and it produces a classifier, and the classifier is a program, and the classifier is given the new example, then it predicts the label. Okay, and we know both from theory and practice that's what is also essential is to understand the source of your examples, and the trained examples come from some distribution, some source, and this is a very powerful phenomenon as long as the test examples come from the same distribution. Now there's the question of how much to make this precise and quantitative. So I'll just argue briefly that one should do that for the purposes I'm trying to do. So this learning from examples can be put in more precise form in this probably approximately correct model of learning, where basically you insist on a quantitative constraint on how well the prediction error reduces with increased effort. So the computational effort involves both taking more examples and computing on these. And what can be shown for some for some simple algorithms, and what is revealed experimentally on actual algorithms that are practically used, is that the errors decrease as some algebraic curve, as some power of n, maybe n to the 1 over n to the minus a half. And so this is a precise definition of learning by example, because it tells you how much you want the error to decrease with more effort. Okay, so of course what this algebraic law says is that if by making 10 times the effort you halve the error, then by making 10 times more effort you'll halve the error again. So it's always tempting to put more and more effort in. You're just rewarded just enough. And of course, this explains why in the world of machine learning, companies with enough money are insatiable in how much they train their models. Okay. So this is learning by example, but just to say a bit more about this. So one reason for looking at the model theoretically is for what it says, what the definition tells you. But I think it's even more important, as important, is what the definition does not tell you. So this definition of back learning I just gave you is about generalization, that you take some examples and you predict something with decreasing error. Okay, so back learning is about generalization, nothing else. Now, if you think informally about supervised learning, then you say, well, look, humans can do lots of other things. We can explain, spurious correlations, adversarial examples. In this conference, in this meeting, we've heard various about outer distribution phenomena. So these are complaints. So these complaints are valid in the sense that humans have some capabilities possibly in doing quite well. But the point I'm trying to make is that these machine learning algorithms we have been trained exactly to generalize well. The ones we use are the winners of 40 years of competition to generalize well. They weren't defined to, they weren't trained to do any of these things on the right-hand side. And in fact, these things on the right-hand side, maybe we need to do other things. And so in some sense, my proposal for the educability model in part does this, that it fulfills functionalities which I think pure generalization doesn't do. So I think generalization in back learning is wonderful, but obviously it's not everything. Okay, so the question is, well, what else is there? So large language models are trained to predict the next token, and they do this in a very scientific way. You know exactly with what accuracy they do it because you can test it, you can predict it. But what else they do reliably, we don't know. And of course, many people here are trying to find that out. Okay, so I'll omit that. Okay, so the second part of the model is training, which corresponds to one kind of reasoning. And the phenomenon here is that in the systems, we've learned from experience. We've done this learning from examples. But what we've learned has some uncertainty invariably, and now we want to reason on it. We want to chain together what we've learned and gather something useful, okay? And so I do have a formulation for this, which I call robust logic. And so the main feature is that you want it to be principled, that when you chain together two things you've learned, you want there to be there's some reason to believe that the result of the training has some reliability. Okay, so soundness in logic is basically this. Here we have to redefine it because it's in a probabilistic context. And as before, we want it to be computationally feasible. So I think this idea of chaining is very fundamental. Living things, as soon as they learn things from examples, from experience, it was stupid not to try to train it, and they must do it in a principled way. It must work reliably. It's not a random event which we can tolerate being unprincipled. Okay, so of course, large language models do some reasoning. So Noah Goodman's talk covered that, but the reasoning is kind of haphazard. Okay, okay. So what I'm describing now sets some standards which also machines may try to emulate. Okay, so So what the robust logic model does briefly is instead of having one single learning box, we'll have many learning boxes. We still are based on machine learning in the standard sense, but we'll have many boxes. Each will make predictions, but we'll have some principled way in which we can chain between them. And when we reach conclusions where we've chained together the various predictions, we should have some reason for believing it. Okay. So just to highlight the importance I give to this, just a quotation which Winston Churchill may or may not have said. He said that true genius resides in the capacity for evaluation of uncertain, hazardous, and conflicting information. So I'm quoting this slightly ironically because the point I'm trying to make is that every animal needs to make the same evaluation. They're faced with hazardous and conflicting information all the time. So everyone must need some reliable way of doing this. Okay, and that's what this second part of the educability framework does. So the standard pack learning framework guarantees generalization in the way I've described. And if you do this robust logic, you get the same, but in addition, you want soundness guarantees when you chain things. So for example, the simplest thing you expect is that if you chain two rules, which are each 99% accurate, and so the accuracy of the rule you can estimate from how much support there is from the training data, for example, or you can test it on data which you haven't seen before, then you want some guarantee that of the accuracy of predictions made from the chaining, and it'll be less, but maybe 98%. So it'll come from union bounds. Okay, so all this, as I said, has to be done in a rich enough domain. So this is just a domain for a crow doing some puzzle, and the idea is that the situations we look at in the world have several parts. So this crow is looking at some glass with some water in it, a seed, water level, some relations, the water is in the glass, etc. So these are the situations we see. And so the hypothesis is that what we're going to learn is our rules which are in terms of this. So the rules we learn will be relational. Okay. And furthermore, in this world, the examples are partial. So it's different from having a million pixel picture where every example has the same million pixels. Here, the examples come from different domains of life with different features, stated and unstated. Okay, so in this robust logic system, there's something called the mind's eye, which basically corresponds to working memory, but it doesn't try to model working memory. It just tries to solve some computational constraints. It tries to get some computation done, and so the idea is that we have a relational world. So actually I call these tokens. So in your mind's eye, you can see a certain number. You have certain number of tokens when you wake up. Maybe these are two of them, and then one token is ascribed to this predicate dog, and likes is a two-argument relation. Dog likes, and then this is your mind's eye. And what happens is that you've got lots of rules which you've learned, which you can call upon in your mind's eye to update your mind's eye to what's likely to happen or likely to be true. And it may be that you predict that what your dog likes is a bone. And so what these rules are which update, so these rules are classifiers. So the rules are like, it could be like a deep network for predicting something, except this network will predict whether this missing object is a bone on the basis of everything else it sees in your mind's eye. Okay, so in this system, you've got lots of learned rules, and you've got a mind's eye where you describe a situation, and then the learned rules which apply to the situation are called upon to update your picture, and you can make predictions, plans, deductions, conclusions. Okay. Okay, so you train in the mind's eye a set of rules which apply to the situation. Okay, so just one comment. As I said, that the system addresses some issues, some broader issues, which the single learning box does not. So several people have referred to this out of distribution phenomena. Okay, so that means many things, but I just want to address one of them. So if someone asks, did Plato own a cell phone? Then you would say this would be an out of distribution example for a standard learning box, because we don't have many. Usually, we don't have many examples of Greek philosophers with their gadgets. Okay, so this is actually, on the other hand, this is something which everyone can answer, and I think how we answer it is by some sort of chaining of rules. When did Plato live? When was cell phones invented, etc. So we can chain these rules. So these rules we learned in separate domains, and we learn them, we believe in them, we chain them together, and this is how we can do reasoning, which in a principled way, which a single learning box would not be able to do if this was out of the distribution. Okay, so this can be explained in a principled way. Of course, your prediction, your answer to this question could be wrong if somehow the examples you've seen in the past life hit some deep truths, like maybe Plato did really have a cell phone. Okay. Anyway, so just one word about quantitative things. So the main thing is that there's a system which I haven't really described to you, which is sound. You can, the principled way, reason for believing in conclusions, and quantitatively, in fact, the number of objects you can tolerate in your scenes. So this is the 7 plus or minus 2 thing. In fact, that's not so critical. The behavior is, the complexity of everything is polynomial in that, so you could build a system with more. So the only bad thing is the arity of the relations. So you shouldn't use primitive relations with very high arity. So the examples I gave have arity 2, and we need to break down relations to arity 2. There's no reason to believe that humans are good at very high arity relations. Okay, so let's go back to the civilization enabler. So the third part, I've described 2. The third part is taking instruction from others. So basically, idea is that we've got all this infrastructure I've described, but in addition to learning from experience and using it in the way I've described, you can also take from someone else, from their brain, a description of the program they're executing, a description of the rule they are applying. So this is receiving explicit descriptions of programs. So it's a bit like being having a universal Turing machine capability on top of the infrastructure I've described. Okay, so educability is the realization, the integration of these 3 capabilities. And so as far as the upside of educability of the last part, well, that's pretty clear and much discussed. So being able to tell other people your discoveries is clearly great, because you may put enormous efforts into making your discovery, but you can just tell them and then a million people know afterwards. Also, some of these discoveries are very general, so I think new ways of reasoning should be discussed in these terms. So arithmetic is a discovery, way of reasoning, probabilistic reasoning, and things like that. So these are discoveries of our civilization. So accumulation of science, and allows humans to go to the moon, complex culture. So clearly being able to transfer knowledge just by telling people is an incredibly powerful addition to a rather complex infrastructure, which I think most of which things we already share with animals. other animals, except for the addition that we can also do everything with symbolic representations. Okay. So a picture version of this is that we live in some environment which is complicated. If we do pack learning for example, then we're kind of adapting to our environment. If we reason, then we're also reasoning with things which are adapted to the environment. And if we reason soundly, then we're kind of safe. We're doing things which are adapting to the environment. But this third stage of actually acquiring some program from someone else is totally ungrounded. So this program could be totally divorced from our environment. It may be bad for us. It's a totally different direction. Okay, so that brings me to just very quickly mention 6 different things which I've started thinking about after having done this work. And the first one follows on from my last comment, is a downside of being educable, which is, as I said, that the basic learning and training, which we share with other animals, are grounded in experience, whereas if you absorb instruction from other people, then you're kind of taking a risk. Because, in my model, I've not included any way of checking whether someone's belief is valid or true. And and as far as I know, it's not that I've omitted it. I don't think evolution omitted it by mistake. I think it's just difficult. So if you tell me what happened on the other side of the world yesterday, I can't verify it for myself. I have to believe you. If you tell me something is a law of quantum mechanics, I can't verify that for myself either. So being educable has the serious downside that we're easy victims of arbitrary belief systems, ideologies, conspiracy theories, and the emphasis here is not that there are these bad guys around who tell us bad things, but the emphasis is that there seems to be a real fault in ourselves, which I think we haven't fully explored. There's a real weakness in ourselves, and somehow it would be good to address this. Okay, that's item 1. Okay, so one question people ask is, how do I become more educable? The answer is, I don't know. It's kind of a new concept, subject for future investigation. But if one claims that you can improve educability, then you would need a test for it. And what would that look like? Well, that's easy, because a test for educability would test for knowledge acquired after the beginning of the test. So almost every test tests for previous knowledge or previous traits. IQ tests usually test for previous traits. This would be different. So the only previous trait this would test for is the one of educability. But you try to just measure how much in the course of the test, the information you're given, you can acquire, use, apply in the sense in which the definition requires it. So I think this would be a new kind of ambition. I know with all kinds of difficulties, but just as examples of what it's not. So in an IQ test, you may ask, if apple is to C, then. Point is, you've learned nothing from this question. You're being tested on some previous relationship. So comprehension tests may be closer, that you're given some information and you're tested on how well you understand it. But again, many current comprehension tests basically test you for vocabulary or your understanding of previous knowledge. Somehow one has to evade that, okay? Okay, the third thing is that this model has, it is a model, it's in some sense a mathematical model, but it's kind of, it's pushing the boundaries because it also has many parameters. Of course, you could say that Turing machine has parameters, the memory finite version has. Machine learning has important parameters, the learning algorithm, the data you've given it. So its educability model has many more. So, for example, this mind's eye, clearly you need some management strategies for operating it. There are many options. So, for example, Seed in the first workshop referred to how different species of different species of monkeys operate their working memory differently. It's basically a different refresh rate. So there are many parameters which you have to decide, and probably there's no optimal parameter. It depends kind of in the environment you live in, as far as I know. Again, a second very fundamental parameter is what I call belief choice. If you're a standalone entity, machine, human, whatever, and you're given information with examples, and certainly if you accept their theories, you have to decide who to trust, who to believe. And there's a vast amount of psychology literature on what humans do in this regard. Okay. So in this mind's eye, you can also make up new concepts by combining previous ones. The question is, what exactly should you do? The more ambitious you are, the more expensive it is. And also another parameter is that, so the reasoning isn't some fixed reasoning system. The reasoning is a chaining mechanism, and this can be informed by particular reasoning methods like arithmetic. Okay, so a very important part of the system is that it won't be able to discover all these different reasoning methods, but you can teach it or program it. Okay, so these will all be parameters. And parameters are not a bug of the educability model, I believe, but a feature of cognition. Okay, so we're all different and in incomparable ways, and our parameters are different, partly by education. Okay, 4. Singularity, much discussed. Will human existence end because of AI? And so the arguments for this usually start with something mystical, like I.J. Good is maybe a good source of where these ideas originate from. And his argument starts, let an ultra-intelligent machine be defined as a machine that can surpass all the intellectual capabilities of any man, however clever, etc., etc. Well, if you're worried about ultra-intelligent machines, then you should maybe worry. But what if you take the view of what I've said, is that our basic capability can be expressed in terms of explicit, prosaic, understandable components. Nothing to worry about, just understandable bits and pieces. And what if this is all there is? Maybe I got the details wrong, but we'll define exactly what cognition is. We can make machines which can do this. Maybe some parameters will be different. And also the main point is that these will have parameters. So it's not a one-dimensional thing of more and more intelligent, but many parameters and no strict ordering. Then I think the singularity argument is much less persuasive and less something to be feared. Okay, so this wasn't intended to annoy people. I'm sure it will. So I've always wondered why social science theories come in different flavors, like different political flavors. So what does that mean? So recently I've also gone into reading some of the eugenics literature and wondered where those people went wrong. And I think there's a serious challenge to scientists, because the people who were pursuing eugenics were very serious. They were quantitative scientists. They defined statistics, the science which is still widely used in certain sciences. So it's very hard to dismiss eugenics. So in reading some of the literature, okay, so the general question, of course, in studying human behavior is that it's hard to draw conclusions about human behavior where the conclusions are transferable in time and space. And okay, and so why is it so hard? Well, I think I found a word for it, and I think it's educability. So the idea is that it's not just saying that we're very subject to nurture, but that we're extremely subject to nurture, and furthermore we can try to spell out exactly by what processes our behavior can change. Okay, so I think it's kind of an explanation of the difficulty of making generalizations about humans. So in one sense it's just giving a word for it, in another it's saying a little bit more. And just lastly, education. It would be nice to contribute some to a more scientific basis for education. So again, here I'm trying to define the components of cognition relevant to education at a more basic level than most other people discuss. So I think this is certainly a direction I'm thinking in. Thank you.
Share your screen. We can see your face. Leslie?
Hello?
Yeah, if you unshare your screen, then we can see you more clearly. Yeah. Thank you. This was great. It was great to actually Les was with us for the last 3 weeks, and it was amazing. In every single session, he would come and have something smart to say. And we even had 2 hours of like a fireside chat with Les where we talked about educability. And still now I learned like twice as much as we talked about then. So this is very, very cool. But okay, let's take some questions.
Hi, Les, this is Shafi. So I have a question on your part 2. When you use the word soundness, in that example, for example, that you were chaining together 2 facts, each one, I don't know facts, but something was 99%, another 99%, and the chaining was 98%. You mean this on the average, right? So distributionally.
Yes, it means that if you take just like in the standard sense, that if you take a random example, then that's the probability of getting it right. Yes.
So what I'm getting to is that in all the things that you discussed, there's no notion of like provability for a worst case. So when I think of soundness, sometimes you can think of it in the sense of a proof, right? So you have a high probability per a single instance on your distribution, and you could imagine, not for everything, but that this is also could be part of a theory, that there are some things that we would have sort of more of a worst case guarantee on, that be associated with a verifiable proof. And then later you talked about this whole notion of belief. So what do we believe really? So the whole, at least within mathematics, we believe proofs, right? There are things that that we can check. They're not everything, but there's a subset that maybe is not grounded in belief, but is grounded in something beyond belief.
Yeah. Okay. So this is use of words. On the first part, the soundness. Yes, I do have a kind of a pack theory version of soundness, and so it doesn't deliver more than the basic pack theory. That it's take a random example. So the probability is over the choice of the example, and that's all the guarantee is in terms of. So that's all. Okay, so the use of the word belief. Okay, good point. So, a belief is basically a program. You can say it's a program. Okay, it could be a neural net as a belief. So belief is anywhere where you you predict something from some other information.
So also a mathematical theorem can be thought of as a belief that we used a way to reason to reach a conclusion.
Yeah, if it makes a prediction, yeah. So some beliefs you could say are true with certainty given the framework. Yeah. So if you believe that between every two the different even numbers and number is an odd number, then that's a belief, and but that's certain. That'll be true with certainty. Yeah. So some beliefs could be true with certainty. But beliefs which are true just in this pack sense, when you chain them, the things don't improve, but you try to make sure they don't disappear. So the guarantees of validity, you don't want them to vanish, but you want them still to have some lower bound of probability of being supported.
Hi there. This is Megan Peters from Irvine. I actually wanted to follow up on the conversation about belief. So throughout your talk, you're talking about how models can have beliefs, and that, as you just said, is the capacity to predict everything or anything. And this is quite different from the definition of belief that's traditionally used in philosophy, which is a propositional attitude. So you kind of need to be an agent that has a mind, that then you can have this attitude that you take a certain statement or a certain proposition to be true. So you have to have the capacity to evaluate the truth value of this proposition in order to be an entity that can possess beliefs. So to take a concrete example, like a regression model is not something that I would consider as capable of having a belief. So I was hoping you could talk a little bit about the difference between the beliefs that we as agents with minds can have and the beliefs as you're defining them that a regression model can have a belief, which feels very, very different to me.
Yeah, okay, so I think what I mean maybe so somewhere in between. So kind of a single belief is, I think, is something arbitrary, something which predicts. But if you're an agent, you collect beliefs, and there's also the issue is which are the beliefs you actually believe in and act on, and which are the beliefs you just store away. So maybe you know how to argue about different political systems. You aren't yourself committed to it, but you can argue about each one separately. I'm not quite sure what view you take of that. We can manipulate beliefs in our minds without committing to them. But certainly, I mean, I sympathize with what you're saying, that if you're a standalone system, then the beliefs you adopt are somehow special, you act on. One would hope that, I mean, first question is whether are they consistent? And so in this system, I can't guarantee consistency, and I don't think we humans operate with consistent beliefs. And I think that's too much to guarantee. So these entities have these programs which have input-outputs. If they act on a set of these beliefs, if they're very contradictory, then it's a very bad situation for the entity to be in. I think it's hard to keep them consistent. So I think your concerns are slightly reflected in this concern. That the concern I do have is which are the beliefs which this entity acts on, and in some sense believes in your sense, I think. But also there has to be room for this entity to be able to argue about the arbitrary beliefs as an intellectual exercise. Okay, so.
Okay, thank you so much, Les. I think we'll take a break now, and we will be back at 10:45 with Alison Gopnik. Thank you.